I'm worried that I will lose the connection.
Okay,
Uh,
no worries.
So I have very bad internet.
Okay, well, it seems
Okay.
okay so far. So
Thank you
so
so
far
much.
so good.
Yeah, good. Thank you so much for attending. So today I would like to talk about wearable sensors in human-robot collaboration context, and this work have been done um, through the DigiTOP project, which is an EBSRC 3 years project. And the main idea or the main goal of DigiTOP is to provide support mechanisms and decision support tools for industries to adopt the digital manufacturing tools. And 2 weeks ago, I think, if I'm not mistaken, we have released the first digital tool to do so. So yeah, after the webinar, if you would like to visit our website and you can check the tool. So now I will start with my presentation for today. So as from the title, I will talk about the human robot collaboration context as one of the new manufacturing equipment. So the outline of my presentation, I will speak a bit about the motivation, why we need human robot collaboration, and what's missing, why we can use for wearable sensors to overcome those limitations. I will talk about the proposed framework we have, our GitHub, and then I will talk about an illustrative example, a simple example to illustrate how we can integrate the wearable sensors with robots. And then I will talk about something called human-human co-manipulation and human-robot co-manipulation as an example. Finally, I will go through the conclusions and future work. So nowadays, there are more collaborative robots. And surprisingly, even though given the current situation with COVID-19, only sector which is not really like impacted by the COVID-19 is the cobots, which indicates that there is a need to improve this kind of technology. So the main problem is to improve the communication between human and robot, and the intuitive way to communicate is usually the speech, doing like hand gestures, maybe the human posture, the body posture, and the facial expressions. But also there are important physical entities when we are talking about human-robot collaborations, especially if you are in a very close distance from the robot, and you would like to do activities like handing over or doing co-manipulation. Then the intuitive way of communication shows some limitation. So we need more. And especially if the human and the robot is in a physical contact with each other, you don't want the robot suddenly to move and might cause injury to the human. Finally, the human-human kind of collaboration give us ideas how to do human-human collaboration, such as understanding how to human move a big piece of furniture around in a structured environment. So as I mentioned before, if we take the robot, like the human-robot collaboration as an example, we see as we see this in this slide, that the exists support framework focus only on the robot here, and you can find all sensory data coming about what the robot is doing, force and torque sensors, the motion, speed, acceleration, even the temperature of the motors, and so on and so forth. On the other hand, especially when we are talking about cobots, you don't know much about the human. as an example, ROS, robot operating system, they have a very good supporting mechanisms for the robot. On the other hand, we don't have the same level of support. So to improve that, we need to include the human data. So what we are proposing here, as I've shown in the previous slide, we are proposing a framework that take the information from the human activities, whether it's physical activities or sometimes it's more like psychological activities, and try to determine what's the human state. Is he reaching muscle fatigue, for example? Is he stressed about the work? Is he already reaching the maximum workload, the mental workload threshold? So if we can identify those, we can program the robot to react accordingly, and we believe that by such a framework, we can answer one we can provide indications on how to answer one of the open problems in human-robot collaboration. Those, for example, trying to understand how the human behave under certain situation in human-robot collaboration scenario. Also, we can provide evaluation for the human-robot collaboration setup, because up till now, you don't know how to evaluate such a setup. Usually or classically, when you have a fixed automation solution, you will measure the your effectiveness by deciding how much energy you need, what's the cost of the sensors, what is the cost of the running the machine on this speed, how many products you will have, and you can work out how useful and you can evaluate the setup. But in a human-robot collaboration, how can I decide if the robot is working next to a human according to the standards? Now you need to limit the speed. So how can I evaluate the collaboration? How can I say this is a good collaboration or not? The third question is how safe it is, and using wearable sensors can help us a lot in indicating any abnormal activities in the setup, and it might be much faster than getting a dangerous activity using like the conventional way. A human might pick up something going wrong much faster than machine in some scenarios. So in order to provide this framework, we need a set of sensors, and this is only an example. The idea here is only to provide tools equivalent to what ROS is providing for robots. We would like to have the same support for the human. And those wearable sensors can vary from using a brain EEG signal, muscle activity like EEG, and facial temperature, and specifically sometimes people are talking about nose temperature, and try to work out some psychological impacts or mapping those wearable sensors into some psychological state of the human. And then if we do that, we can then program the robot to react accordingly. The examples we have, for example, the cardio signal, which can indicate stress, mental effort, and many others. Also, the brainwave can indicate the drowsy, relaxed activity and focus states. And also, you can pick up abnormality situation using the brain waves. The nose temperature, which is sometimes it's funny how you can measure that, but you can use a thermal camera to do such thing. The nose temperature can indicate the mental workload, and but it's not only about measuring those physiological states, you can also measure the physical activity of the human while it's doing a co-manipulation with the robot. We need to know how much forces are going through this activity. And if the human is grasping firmly on an object with the robot, then this might indicate that the robot is not reacting correctly, and we need to modify that or improve the robot reaction. Again, as an example, those are the sensors we have integrated with our setup. We use MyAware muscle activity sensor. We use the Moose headband for the brain activity, which is a commercial sensor, and with a good accuracy. At least in the literature, they are saying it has a 95% accuracy in comparison with the more sophisticated devices. And we have the cardio sensor, the pulse sensor, which goes to the earlobe, and we have here on the helmet we have an IMU to measure the head movement. And those are the MyAware here, the black and blue boxes. The little boxes are the muscle activity for left arm and forearm, right arm and forearm as well. And we have the thermocouple for the nose temperature. So getting all those, communicating to a mobile data acquisition box, which is basically a Raspberry Pi. And through Wi-Fi, we connect this to a stationary workstation. So to make those sensors work together, we need the software. And the software we have developed is ROS based, and it's a ROS package which can basically it's customized messages, topics that like a carrier that carry the topics from different sensors and try to publish them in the ROS network. If you are not familiar with ROS, basically you can think about ROS as a network of publishers and subscribers. And each sensor here is a publisher which publish a certain message with a different frequency. And because we are using ROS has a lot of support. It's open source, and there are a lot of mechanisms that you can use. One of the interesting things that you can synchronize different messages coming from different sensors, and then you can use this synchronized messages to control the robot. There are a lot of restrictions and limitation of that, but it's possible to do. The software we have developed, it's available on GitHub. And you can find it if you search for Intelligent Automation Center, Blue Box, or if you go to the DigiTOP website, you can find a link for our GitHub. It's an initial effort. It still needs a lot of refinement and improvements, which I'm trying to do in the near future. But feel free if you think it's useful. Feel free to send me comments, and I will try to accommodate any feedback. As an illustrative example to show what I have mentioned before, how things will work together with an industrial robot, we have this example, which basically we have a human operator with the wearable sensors, the muscle activity sensor on the left and right arm. And we integrate that with an industrial robot, 6-axis, 6 degrees of freedom, and it's a UR10 collaborative robot. And we have this simple logic, and there is no scientific contribution in that, but it can be replaced with more sophisticated control approaches like reinforcement learning. And then if the human activates the right arm, the robot will go to the y direction, positive y direction, 5 centimeters. If he activates the left arm, it will go in the opposite direction. This is the video of the setup and the experiment. Again, it's not like there's no massive scientific contribution. It's only to show how things are working together. I hope that this gives you an idea. Again, this video is also available on our website. So the messages which is come through the provided packages can be seen here as a list of sensory data. And what I would like to show you here, that we have the force torque sensor coming from the robot, and we have and originally it's 100 hertz. But when we synchronize this with the muscle activity, it will go up to almost 90 hertz, which is not great, but it's sometimes especially with noisy data like the force torque sensor, it works like a low pass filter. Now, in the second part, I would like to talk about the human-human co-manipulation, and this is like a continuation of my PhD. So when I've done my PhD, we have done a co-manipulation between two humans, and we try to collect data from the positional data from a beacon system. We collect the force torque data using this setup on the left side. And then we try to use data-driven approaches to understand or map the displacement of the object with the force clues, which is coming from the leader. The human on the right side is leading the co-manipulation. The second human on the left side is a follower. And as a result, we wanted to validate how accurate the algorithm was. We did a co-assembly task with multi-bigs, but with a massive threshold, with a massive clearance, because this is a pure force-based. There no vision, and did not have any other algorithms to react to external forces. So and this was the result. So the interesting bit about this, and you will see at the end of the video, that once the insertion happens and the operator remove his hand, the robot will move due to additional contact with the object. And this is something not desired. If you are working on with the robot, and you release and you guide the robot to do a task, and you release the robot's arm, you don't want the robot to react to any other external forces. What happened here, that after the operator released the hand, the robot moved back and almost break the parts. And this is where using wearable sensors can be useful. If we have muscle activity sensors that indicate the human is not doing anything right now, and then the robot should not react to this. Another example, which is not as I hope it will be obvious, but this is also part of the same experiment. So when the human is trying to guide the robot to do a certain task, if you have any external load, like now, the robot will still move. This load, you can think about it as a dynamic load, which have been added to the robot, but still the robot is reacting to the load, which is something not desirable, because this means that you might the robot might go to damage the part, or might cause a damage to the human. So in this, as part of DigiTOP, we have collected data in a different way this time. So the concept of a human-human co-manipulation can be mathematically represented as a mass spring damper system from both sides, and then it's a simple mathematical problem in 3D. But the problem here that we don't have much of information of how much the forces from the follower and from the leader. So we design a setup where we have a force torque sensor, we have a load, and we have a follower with the muscle activity, and the leader will hold the force torque sensor and guide the load through unstructured environment. We have only one obstacle in the middle, and the robot or the two human are trying to avoid it by guidance coming from the leader. The data have been collected, analyzed. We remove the noisy data. We try to filter the data, and it's available on this website, on the University Repository, and anyone can use the data if it's useful for your research. And then again, we mathematically try to come up with a concrete definition of the problem. As input, we have force, we have EMG signals, and as output, we have a displacement on X, Y, Z. We didn't consider the rotation of the object. And then our problem in this case, it's a mapping of this input into those outputs, which is somehow for computer science, it's a regression problem. So we try to use different data-driven approaches to extract this mapping, and we try to compare that with a mathematical model. So we use a set of features, and the set of features are basically the normalized force torque sensor, normalized EMG, and the historical data coming from like the previous displacement of the object, because this problem is a temporal problem. It depends on how much you have done displacement previously. So we thought that it would be a good idea to include that. And then feature 2 is like the set of features 2 is without the EMG. The third set is with the EMG and unnormalized EMG and the displacement. And the fourth set of features is normalized FT, EMG, and the previous displacement. Then we use those data-driven approach, linear regression. It's one of the simplest way to try to find the mapping. It's not, we know it's not suitable, but it's still an easy way to do it. A random forest, which is also, the concept is simple and it's a very powerful mechanism. Gradient boosted trees, and then we use deep neural network, recurrent neural network, and again, I thought we come across this slide already. This is my mistake. I'm sorry. And the collected data, we had 5,000, almost 5,000 data points, and we have 5 trials. The obstacle was in the middle here, and the two humans were trying to avoid that using this trajectory. This data were collected just before the lockdown, so sadly we couldn't carry on the data collection, but we thought that we can carry on with the other work. Hopefully soon we will be able to do the rest of the data collection. So briefly, the results of what we have done, we, as you can see, some of the data-driven with the EM, it does not make big difference. This is the RMSE in centimeters for the linear regression model, random forest, and boosted trees, and recurrent neural network. As you can see, the recurrent neural network has the best performance with the feature set 1. Then you have the random forest, boosted trees, and as expected, the linear regression model. But we thought that in comparison with the mathematical model, it will be a good idea. I know this is kind of a different research, but we thought that we can combine the neural network the recurrent neural network with the mathematical model to do something called hybrid approach, where we combine the mathematical model and the data-driven model to see if this will be any use, especially to improve the mathematical model performance. The mathematical model performance, the error is almost 1.7 meter, which is massive. And you can see all the data-driven model is the error is less than 0.25 centimeters. The hybrid model, where we combine the data-driven model to model the error of the mathematical model, it was also not bad in comparison with the mathematical model. So if you have any question about this, I try to quickly run through those approaches and the hybrid. But if you have any question, please let me know at the end of the presentation. Finally, I would like to talk about the conclusion and future work. So in general, what we have seen here, that there are still some questions about human-robot collaboration setups. And we believe that wearable sensors and trying to extract the human physical and psychological state will be helpful to improve the human-robot collaboration. The problem research in the literature, people have done research on one sensory data and they integrated and it's good, but we still lack a more holistic representation of what we need in human-robot collaboration setups, and what data will be useful, what data will not be useful. So because of this, we have presented our initial framework to support this effort. And in the future, we would like to improve that by including more sophisticated control methods like reinforcement learning, interactive reinforcement learning. Also, our tool lacks a lot of visualization tools, and we would like to extend that in the near future. Thank you so much. That I didn't go through the things quickly. If you have any question, please feel free to ask.
Yes, Ali, thank you for that presentation. I have a question. So it's very interesting. Particularly, I was thinking about the manipulation task. It sounds to me that looks like a very good option for including like a glove with 4 sensors embedded in there, or something like that. Or
yeah, there are.
That to me sounds like well, certainly the problem of well, you put this roll of tape on there. Another option is just use motion tracking, form of motion tracking. Once you know the outline of the robot, you can kind of estimate whether there's contact or not with the human.
Yeah, there is the gloves is already there are people who are doing research on that and integrate that with the robots. We tried to get one of those gloves, but up to now we haven't been successful in our center. But I honestly I hope that I will be able to include that. The vision, yes, the vision can provide answers, can provide some information about the current situation. However, and we have experienced this ourselves sometimes. If the human is too close to the robot, using vision system, sometimes it's confusing to know if the human is still in touch with the robot or not, and you still need a kind of a contact sensing equipment to indicate if the human is still in contact with the robot or not.
No, Yeah, so I would assume that the video would be more of a rough kind of proximity sensor, more for like body parts, rather than of course it's not sensing like the force or anything. So
yeah.
Yeah.
Yeah, I agree. It depends on how many cameras you would like to integrate in your system, how much computation power you have also. So those variables also contribute a lot into answering what is the suitable setup for human robot collaboration. I it it and this is one of the open question in the human robot collaboration is how much I would like to invest in that. The force and torque sensor and the muscle activity is a very cheap solution in comparison with 12 camera system with a set of GPUs and deep learning in the background, trying to extract the open posture of the human, like software. So I agree it's useful, but in close to contact situation, it still lacks the information.
Yeah, I guess it's about whether the application search for is generalizable or not, right? So uh, uh, if it's a very constrained task like what you were describing, then of course you want to try to search for the sensors that are as specific as possible to the task that is being asked. But if in the future the manufacturing floor has robots performing multiple tasks, and then it's likely that yeah, a lot of different options need to be available, and also there needs to be adaptability based on the task, of course.
Yeah, I agree. Yeah.
And sorry, just to follow up on that, the question as well is like what approach do we take, right? So is it just keep adding sensors, because you in your example used I think four EMG sensors, but yeah, we could add many more. We could, or do we do that, or do we try to improve the computational side of things, or both? Right? So I mean, that's still a question. I kind of reiterate the point you're making at the end, is that, yeah, I mean, at some point there's going to be a bit of a bottleneck, I think, in terms of data bandwidth. More data is not always better.
Yes, yeah, but we need again. I think I totally agree. But we need to, in order to decide what data we need first to combine all of them and study all of them, how they are react with each other, find the relative mapping, and then remove the sensory data which does not improve the setup. But first we need to do that.
Yeah, I think I would argue you could make some educated guesses based on. So I come at I'm not an engineer myself. I come at this from the angle of the human. I'm a human movement scientist. So I would argue that data about humans can probably guide you already a little bit on what types of sensors that is, whether it's kinematics, whether it's forces generated, how useful those bits of information are to to convey what the human's actually doing.
Yeah, I totally agree. Yeah. There is I think you might be you know about that more than me. There's something called error related potential, and this is basically your brain can indicate if there's something going wrong in your environment, and if you can pick up that, then you can use this signal to teach robot to do things and do a corrective actions based on this signal.
Yeah.
So yeah, I think using the human in this in such setup is very useful. But there are a lot of limitations. So hopefully in the future we will be able to.
Well, we don't know everything about the human yet, so that's
Exactly.
keeps me in work.
Okay, do we have any more questions for Ali?
Oh, hi. I have a question. So it kind of follows from the previous discussion. And it's although it's not my area, but I'm interested if you've at all considered at any point or have plans to consider sort of the human acceptance of wearing all of these sensors, and if you sort of have any ideas about what to do about this research and on this topic.
So yes, so we are, sorry, I forgot to mention that we are working with Nottingham, Bristol, and Cranfield. And I think in Cranfield, if I'm not mistaken, they are doing the technology acceptance studies. It's not my background, so I don't want to talk about it. But yeah, it is definitely relevant. And as like DigiTOP as whole is looking at those things. I'm focusing on this kind of applications, but it's within our interest.
Oh, thank you very much.
Yeah, welcome.
Okay, so thank you, Julia and Joost, for your questions. If anybody has anything else, please do shout. Otherwise, I'd like to say thank you, everyone, for attending today. It's been really nice, and it's been great to hear about everything from you, Ali, as well.
Thank you so much.
Thank you. We are going to put this recording on our DigiTOP website. So if anyone would like to use this and access it, that's absolutely fine. And we also encourage you to have a look at the DigiTOP toolkit, which is in its very first stage of development. There is some information on there. There will be a further phase next year where there'll be much more information released from all the studies that everyone's been doing in the team. And if you have anything that you want to speak to the team about, then please do get in touch with myself, and I can always pass any messages on, and we can make those connections with you guys as well. So thank you very much, everyone, and I hope you enjoy the rest of your day.
Thank you very much.
Thank you. Take care. Bye.
Thank you. Bye.
Thank you. Bye.